In this video, I want to talk about some more maybe general ideas when it comes to solving a reoccurrence. So for us, we got reasonably lucky. We had a recurrence, right, when we were able to solve it. So a solution did exist, and that solution wasn't too complicated. That is, a lot of luck there, right, just by itself. The other thing we got lucky with is this basically process where we said, okay, I can basically make a chart of the values that this exists, that this recurrence generates, and then from that, go and guess a particular function, right, that might model that, right? So we guessed that to the n minus 1. We did a proof, and we found out, hey, those two things match up. So basically, we were able to guess the answer. So that's great. The problem is it basically never happens like that in practice. Usually what happens is we do that chart, right, and all of a sudden we see a sequence of numbers, and it's not really clear to us how those might be modeled, right, or how they might be related. Maybe we could try things like grafting it, but really it'll be kind of hard. Those numbers may not have kind of a clear pattern, right? So what do we do? There's kind of 4 general methods you can maybe think of. The first, right, is just guessing. So maybe you do get lucky. Maybe you are looking at a tower for noise style problem, where just from the chart you can basically say, oh, hey, it looks like it could be this function that models it. Maybe try that and then use induction to prove that's true. So that could happen if we get really lucky. The other thing we could do is use something called the master theorem. So this is actually something from the MIT algorithms textbook, CLRS. That particular textbook, they give this method where basically they say, okay, if you have a recursive function that looks like this, right, has maybe this number of recursive calls, and they work on this size of a subproblem, it'll give you basically a formula where you can plug in those coefficients to describe your algorithm, and the theorem will basically have a way well, it'll be evidence, right, that based on what you put in for the coefficients, the particular order, right, you'll find a particular order for that growth function for that particular method that you're analyzing. So it's basically a plug and chug way, right? We put in the coefficients for how the recursion works, if you would, and then gives us back a growth function, right, or gives us back a big O. So that's nice, but problem is our functions, right, our recursive functions have to look a certain way. Well, I should say recursive methods, right? We're talking about code. So it's useful sometimes, but sometimes you end up maybe having to manipulate your code in order to make it fit that theorem, right? Make it fit that formula that'll tell you what the recurrence solution it will look like. A third we can do, right, is there are maybe some big tables that'll show you, okay, hey, if I have a recurrence that looks like this, this is what the closed loop or closed form version of it is. So you can think back, right, you also know about, there's tables of integrals, table of sums, table of products. There's also tables of recurrences. So you could maybe think about using one of those, but again, that's a lot of work and it's kind of annoying. Well, last thing we can do, which is what I'll tell you to do, is just use a CAS. So basically, write your recurrence, throw it into Wolfram Alpha, find out what the result is. We really don't need to spend our time analyzing that thing. Just make the machine do it for us. That'll be better. So one final note on this idea of creating closed loop formulas for recurrence. We can actually generalize it a little bit. So let me ask you guys the following question. Think about the problem of computing the Fibonacci sequence. How hard is that to do? So typically what people start with is they start with a recursive algorithm for it. So it's an algorithm that basically you make 2 calls every time you want to evaluate the formula for a particular entry. And that ends up basically taking a long time. It's something that, if we were to analyze it the way we've been analyzing codes in this section, we'd end up with something like an algorithm that's to the n, because basically every time you try to go and evaluate the nth Fibonacci number, you need the n minus 1, n minus 2 Fibonacci number. So we just kept on growing and growing and growing. Every time we want to analyze something, we basically have to double the amount of work we need to do. So think about that for 1 second. And then ask yourself the following. Can I make it faster? One thing that might come to mind is maybe putting them all in an array, right? Maybe I have an array where the first entry is the first Fibonacci number, the second entry is the second Fibonacci number, third entry is the third Fibonacci number, and so on. If I do that, I can basically have a loop that goes along and populates each of those. So all of a sudden I've gotten rid of all my recursive calls. I basically just have to compute the value of each entry in an array based on the 2 previous entries. So that's fine, right? That's actually going to be an O of n algorithm, because I just need to go and fill in each entry one by one. But can I do better? Think about that seriously for just one moment. Can I compute the nth Fibonacci number in less than O of n operations, right? Where the number of operations is maybe something like a addition or subtraction or multiplication, right? Just some computation. So think about that. Is it possible? So the answer is, of course we can do it. Otherwise we wouldn't bother talking about it. So what we have here is a little bit of magic for once. So this is a formula, a closed formula for computing the nth Fibonacci value. I'm going to highlight the variables there. So Fibonacci, right, maybe we think of normally in terms of a recurrence, right? So Fibonacci of n equal Fibonacci of n minus 1 plus Fibonacci of n minus 2. For the record, I'm trying really hard to write on the screen, but it just doesn't work for me. If you guys have seen any of my videos, you know that the writing just does not work. So just pretend that says f of n equal f of n minus 1 plus f of n minus 0. It's minus 2. Just pretend that, right? So suspend your disbelief for a second there. That's how we maybe typically think of Fibonacci numbers, right? And that kind of formula, right, the best we can do with that is to have some sort of a linear time algorithm for computing each of those values. But what we can actually do is we can actually say the following. Hey, this is a recurrence. So what I can do is I can apply my same ideas that we talked about before, right? Some general ideas, right, for solving these things, and actually take this and create from it a closed formula, right? And so this closed formula will let me compute any Fibonacci number just with some additions, some divisions, and a floor. And so I'll basically get a Fibonacci number in O of 1 time. So this is another basically application of creating these closed solutions to recurrence, right? Is that there are some maybe problems we can solve in linear time by collapsing down the recursive formulation. And so there's a lot of problems, right, either in math or computer science that basically can be expressed as a recurrence. And so whenever we do that, we basically have this idea, right, or this chance that maybe there is some way to reduce it to this closed formulation, right, which we'll be able to analyze or be able to basically evaluate in O of 1 time versus our complete thing, which is O of n, for example. Best case, right, with some optimization we get to O of n. A naive approach over here, right, would be 2 to the n. So we have basically this way to optimize things. And it's really nice. So what's happening behind the scenes is well, it's magic. Okay, so just assume that what lives in this formula, right, this formula for f of n that's closed, is basically magic. Because we don't have a lot of time to discuss it. If we had another semester, a whole semester, another 135 hours, then maybe we would have a shot at describing what happens there. But to kind of give you an idea, what happens here, right, is that this function, we can basically put in a value for n and it computes something, right? We take the floor of it, magically we get a Fibonacci number. Somehow what is happening is that the kind of the character of the sequence, right, the nature of the Fibonacci sequence, right, the fact that every value is computed by the previous two, that is being encoded in the series of operations in that formula, right? So that entire sequence basically lives there, right? It mainly lives in the phi, which is a special constant that you can compute offline. But that general kind of that sequence, right? That sequence actually lives there in basically those different operations. So the influence, if you would, of us moving along the Fibonacci sequence, the influence of that, right? That notion somehow of doubling is encoded, right, in the fact that we have phi raised to some power. The division and subtraction and addition, right, are required as well, basically to get us a proper kind of alignment with the sequence. But that magic kind of phi number, which I should have put the formula here. If you want, you can go look on the Wikipedia page. It'll be listed on there. That formula, right, is a closed formula, basically based over normal arithmetic, right? There's no kind of recurrence involved. That captures somehow the flavor of that doubling nature of Fibonacci, right? Basically, again, think of it as just being magic. So this is actually kind of a general area. There's something called generating functions that they study in math. Basically, the idea is for a sequence, right? And the Fibonacci numbers, they are a sequence. For sequences, it's nice if we can basically write a function which basically the parameters to it will specify which element in that sequence we compute. And then it's kind of assumed that I do that computation in linear time, right? It's just a formula I evaluate, there's no reoccurrence. And so that's an entire area, right? Basically coming up with functions that I put in as an argument, which member of the sequence I want, and then it'll compute for me what is the value of that member, right? And those are called generating functions. So that's kind of another way to do optimization, right? Basically, if I have recurrences, right, I can close them up, right, using the generating function and evaluate them in linear time. So this is just an FYI, a lot of stuff you guys won't have to worry about, but there's kind of a little of magic, right, that is possible here. We just don't have time to talk about it today.